As you have seen, the standard deviation directly relates to the ability to predict our arrival time. In a very similar way, the standard deviation also relates to our ability to meet requirements. If the requirements set limits at one standard deviation away from the target, 68% of the time the process will produce outcomes that meets the customer's requirements. In this case, the capability of the process is not good. If the requirements are 2 standard deviations away from the target, the process outcome will meet the requirements 95.4% of the time. Better yet, a process with a smaller standard deviation so that the previous requirements are 3 standard deviations away from the target will produce acceptable outcomes 99.7% of the time and produce undesired or unacceptable results 0.3% of the time. Therefore, the more standard deviations that can fit between the requirements, the better our ability to predict the outcome, and the better chance that the outcome will meet customer requirements. This concept will be extended in Six Sigma methodology to evaluate the ability of a process to meet requirements. We will discuss this concept in details later. Click Next to continue. Now back to our commercial loan process. Remember the histogram we derived after collecting the data? Let's take a closer look at what it tells us. The mean is a little over 61 hours, which is 13 hours higher than our target of 48. Out of 1,393 recorded cycle times, only 7 were below the 24-hour lower specification limit. However, there were 298 cases where the time exceeded the upper specification limit of 72 hours. The standard deviation for this process is 13.7. This process looks, at first sight, to be in serious need of improvement. Click Next to continue. There are several related terms which you must comprehend before you can continue. The first is process capability. The process capability measures the ability of your process to meet customer requirements. It takes the customer viewpoint and applies it to an analysis of your process. Using the cycle time histogram as an example, the process standard states that it should take no less than 24 hours for an application to go from acceptance by the data entry associate until it is ready to be submitted to the credit bureau. This is to allow for review and validation of the form. Likewise, the standard calls for an upper specification limit of 72 hours to complete the cycle from acceptance of the initial form by the data entry associate until it is ready to be submitted to the credit bureau. Exceeding this time negatively impacts the ability of GE to deliver funds on time. The area under the curve outside of the specification limits, as a percentage of the total area under the curve, represents the percentage chance of a non-conformance in the process. This indicates the likelihood of producing a defect from the customer perspective. This technique essentially provides a measure of the capability of the process to meet customer requirements. We have a rigorous system to calculate this capability in Six Sigma practice. The customer acceptable variability is defined by a specification. When we compare our process capability to the requirements of the specification, there are a number of values which may describe the results. While there are a number of these capability indices generated, General Electric uses the Z-bench, often called the sigma level, which can be presented as either a short-term Z, called Z sub ST, and a long-term Z, called Z sub LT. The Z values are the common communication language on process capability. But what do these Z values have to do with our process? Click Next and we'll explore them. The percentage of area outside the specification limits represents the probability to produce an outcome that does not meet the customer requirements. This is the defect rate. Given the mean, standard deviation, and specification limits, you can use mathematical manipulation to calculate the defect rate. This can be very cumbersome at times. Luckily, every normal curve can be normalized by setting the mean to 0 and constructing a scale in standard deviation units. This standardized structure then allows us to use one simple table to determine the defect rate by looking at parameters called the z-scores. The z-scores are calculated by subtracting specification limits from the mean and then dividing by the standard deviation. In other words, the z-score measures the distance between the mean and the specification limit in standard deviation units. Once the z-score is calculated based on this simple formula, one can easily resort to the single-tail z-table to determine the defect rate or the probability of producing an outcome that is outside the specification limits. Let me show you how the z-table works, and then we will perform the calculations for this example. The mean for our example here is 8.5. The standard deviation is 0.1. Now that we have the actual measurement scale matched up with the standard deviation scale, let's take a look at the z-table. This is the z-table. The left-hand column and the top row contain the z-score information. The rest of the chart consists of the probability of producing a defect in the process, which is often referred to as a p parenthesis d. Now let me show you how to use this table to find a defect rate, or p parenthesis d, of a z-score of 1.85. Move down from the z column until you reach 1.80, and then move across the upper heading column until you reach the heading 0.05. The intersection of these two values is 0.0322. which is the defect rate, or p parenthesis d, of 1.85. In other words, this means that there is a 3.2% chance that this particular process will produce a defect at any given time. Before we leave this table, there are two more important items to know. The DPMO, defect per million opportunities, is found by multiplying the defect rate p parenthesis d by 1 million. Both DPMO and p parenthesis d are important parameters in calculating the Six Sigma level of a process. This table can be used in a reverse manner. For a given DPMO, one can identify the corresponding z-score by reversing the procedures that we just practiced. For example, what is the z-score for a DPMO of 93,400? One should divide DPMO by 1 million to obtain a p parenthesis d of 0.0934. Locate the p parenthesis d of 0.0934 on the table. Read the z-score by adding the headings at the top row and the left column corresponding to this p parenthesis d. In this case, the horizontal line reaches 1.30 at the left column and reaches 0.02 at the top row, and thus the corresponding z-score is 1.32. Finding the z-score for a given DPMO comes in handy when we start estimating the process capability in sigma level. Now that you have learned about the z-score and the z-table, let's see how this applies to calculating process capability in Six Sigma methodology. The graph shows the distribution of all possible outcomes for a given process. The mean and standard deviation of the outcome distribution are 8.5 and 0.1. The upper and lower specification limits are 8.2 and 8.7 respectively. To calculate the process capability of this process, we need to calculate the z-score against the upper and lower specification limits, z sub LSL and z sub USL, using the z-score formula that we have learned previously. The z sub LSL is calculated by subtracting the lower specification limit, which in this case is 8.2, from the mean of 8.5, and dividing the result by the standard deviation of 0.1. This results in a z sub LSL of 3. Similarly, we subtract the mean from the upper specification limit and divide by the standard deviation to provide a value of 2 for the z sub USL. Now we must look at the areas under the curve outside of the upper and lower spec limits. Those areas define the probability of the process producing a defect. By calculating those values, we can determine the z-bench for the process. Z-bench is simply the z-score with a total p parenthesis d. Here is the z-table again to determine the defect rate, or p parenthesis d, for z sub LSL of 3.0. Move down the left column until you reach the entry 3.00. Then move over one column to the right, under the column heading 0.00. The entry in that column is 1.35, E minus 003, or 0.135%. This indicates a P parenthesis D, or probability of a defect of 0.135% by falling below the lower spec limit. So we have our value for the lower spec limit. Next, we need to determine P parenthesis D for a Z sub USL of 2.0. Move the Z value of 2.00 on the left-hand column, and then move over one column to read the P parenthesis D for the upper specification limit. This number is 2.28 times 10 to the power of minus 2, or 0.0228. If we add those two numbers together, we get a value of 0.02415, or 2.42 times 10 to the power of minus 2, which is the probability of producing a defect by violating either the lower or upper specification limit. This is the overall probability of producing a defect in this process. Remember the conversion of P parenthesis D to DPMO. This P parenthesis D is converted to a corresponding DPMO of 24,200 by simply multiplying 0.00242 with 1 million. To complete the calculation, we need to figure out the Z-score corresponding to the P parenthesis D of 0.00242. The closest we can find is 2.44 times 10 to the minus 2. Moving to the left, we find the first part of our Z-bench is 1.90. While moving up, we find the rest of it is 0.07. So our Z-bench for this process is 1.97. or about a 2 sigma process, and the corresponding DPMO is 24,200. Click Tell Me More for a full-size printable version of the Z-table, or click Next to continue.